Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good to hear. Okay, so we're in our final week. So I do want most of this week just to be just project workshop time. And so I know a lot of you guys have already gotten started on the final project. And so if you are running into issues with the code, now is the time to kind of discuss it. And so today, what I want to do, I do want to finish up a couple things today, though. So first thing, I did want to finish up our lecture notes on isoparametric elements. There's just a little bit more to go. And so I think for the most part, just for the sake of time, I'll finish writing the algorithm, but the example that I'm going to discuss, I'm just going to show the notes for it and then just kind of go through each of the steps, right? So the example that I have is just going through the same steps in the algorithm, but with actual numbers, right? And so, just so that you kind of see it all kind of in action, okay? So I think I'll go through that fairly quickly. Next, just because it's been a while, I know, I posted the final project thing maybe only close to like a month ago, but it's been a while since we've discussed it, so I do want to review that just very quickly, just so that we're all kind of on the same page in terms of what the expectations are. And then after that, hopefully for the last 30, 40 minutes of class today, it's just going to be open office hours. And so if you're having issues with your codes, you're having trouble getting to run, the errors that you're getting are very high. Now's the time to ask questions and then get your answers, for the project. Okay. And then if all goes according to plan, then Thursday will just be project workshop. So I won't have anything more to say. Thursday will just the entire 75 minutes will just be, you guys working on the project and me just going around just helping people as fast as I can. Okay. With that said, I do want to notify you guys of my office hour schedule for next week. So for this week, two of my office hours have already passed, and so Monday, Tuesday office hours are already done. I do have one more office hours this week on Thursday. Okay, so that's Thursday, May 7th. So we have Thursday, May 7th. Okay. And that's 1 p.m. to 2 p.m. Okay. So you can come to my office. My office is E220, or you can join on Zoom. I think probably for grad students, I think you guys Zoom is probably the better option just because I know some of you guys are working during the day. 1 to 2 p.m. is not the best time period for that, but Zoom is available. Okay. And next week, even though next week is technically finals week, we're not going to have a lecture next week. I am still going to have my regular office hours scheduled just for you to come and ask questions, on the final project. Okay. And so that is Monday. What day is that? Miss May 11th. Okay. So my Monday office hours are 2:30 p.m. to 3:30 p.m. Okay. I have Tuesday, May 12th. May 12th. Also 2:30 p.m. to 3:30 p.m. And then next Thursday as well. Thursday, that's going to be May 14th, 1 p.m. to 2 p.m. Okay. Okay, so office hours regular next week, even though it's going to be finals week. So if you have questions on the final project, that is your time to ask. If you can't make any of the office hour times, just let me know. I am generally pretty flexible during finals week. I have a few other things going on, especially with advising. But if you need to meet with me and discuss your project, you can just email me and then we can kind of set up a time. Okay, so generally, oops, there should be 2:30 for next Tuesday. I apologize. So generally what I would ask is that, if you want to meet with me in office hours next week, just go ahead and propose a time at first. I think generally your guys' schedules are probably a bit more rigid than mine. So if you guys can email me and say like, hey, are you available to meet? Let's say, like Tuesday, 5 p.m. I can probably make that work. Okay. But if we have to go back and forth a few times, so it's where it's like, what's your schedule? What's your schedule? I think I'd rather you guys just kind of propose a time and I'll tell you if it works or not, and we can kind of work around that. Okay. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's finish our discussion of the isoparametric algorithm. Okay. So we started talking about that last Thursday. Okay. So, and this is all just recreated from the notes as well. In fact, I think a lot of you have kind of found this section in the lecture notes, and have used it as the basis for your project. Okay. So this algorithm, the way I've kind of written it in the notes, I've kind of written it in the form of like a pseudocode, where you can basically take these exact steps and just directly implement that into code. Okay. Now you do have to kind of translate. So this is kind of, I think we discussed last week, pseudocode is basically, it goes over the logic and steps in terms of what a code needs to accomplish, but it does so in human language, right? And so it's going to be up to you to basically take this algorithm and convert it into MATLAB lines of code. And if you need help with that, you can always ask for help. But I do want to go through the several steps just because, isoparametrics it's not a, it's not a simple algorithm. So there are quite a few steps involved in it. And so I want to make sure I outline all those steps, just so that you kind of know exactly what you need to implement in the code. Okay. Okay. Step one. Step one is to establish the Gauss coordinates for this particular point. Okay. And so when you write your code, and I think if you've seen the starter code, you've seen this as well, right? When it comes time to assemble the element stiffness matrices, first of all, there's a loop, which is going to loop over all the elements in your mesh. But then within that loop, there is another loop where you're going to loop over all of the Gauss points. Okay. So this starts from that loop, right? So we're kind of starting from a point, we're assuming that we're starting from a particular element here. Okay. And we're writing a loop to visit all the Gauss points in this element. Okay. Okay. So step one here. So now that we're inside the loop for the Gauss points, first step is we need to establish what the Gauss coordinates are for this particular Gauss point. Okay. And so this is going to change every iteration of the loop, right? But for example, let's say that we're doing the first iteration. First iteration, our Gauss points are epsilon equal to -1/√3 and eta equal to -1/√3. Okay. Okay. Step two. After we computed after we've established the Gauss points, step two is to compute the values of the shape functions. Okay. So all of our shape functions have explicit values. You're not going to use these ones for your final project because remember, your final project uses triangles. But for this algorithm here, we're using the quadrilateral. So that one has different shape functions. Okay. We'll review the triangle at the end of class today. But you need to basically plug in your Gauss points into these functions here to compute the shape function values. Step three is to do the same thing, but with the shape function derivatives. Okay. Okay. So steps 1 through 3 here. So 1, 2, and 3, we've done all of these without knowledge of the particular element that we're looking at. Okay. So step 1, 2, and 3, they're basically the same for every single element. Granted, you're gonna have different Gauss points for the different different locations, but steps 1, 2, and 3, same for every element. Okay. Okay. Step 4 is when we start to kind of differentiate them a little bit. So step 4 is we need to compute the corresponding physical coordinates at this Gauss point. Okay, so I think we cut off our discussion here last time. Okay, so let's go back up to our figure for the element here, right? So remember, the whole point of isoparametric elements is that we have some kind of element in the physical space, right? Right, so our element might look like this. So this is the element in physical space. And then what we're doing is we're performing a change of coordinates in order to get the element into isoparametric space. Okay. All right, so what does that mean? So that means every single point in our parent domain, in the isoparametric domain, has a corresponding physical point as well. Okay. So this Gauss point 1 here, right? All right, so our -1/√3, comma 1 -1/√3, this one has a corresponding location in the original element, right? So this has some x, we call it xg, yg, okay? Right. Because when you perform a change of variables, basically every coordinate or every location or every point in your original element has a corresponding match in the new domain, right? So we're doing basically a what's called an onto coordinate transformation, okay? So we want to find out what the coordinates of that original point is in the original element, okay? And so to do that, we're going to make use of two things. And so we're going to make use of the coordinates of the nodes that's read directly from our mesh, right? So we have x1, x2, x3, x4. Those are the physical coordinates of the vertices of our element, right? So that's something you can read directly from your mesh, right? And so you can do that in the final project as well. And then you're going to multiply those by those corresponding shape functions for those vertices, right? So n1, n2, n3, n4. Okay, so we computed those in step 2. Okay. All right, so that's good there. Okay. In fact, you can basically do this as a matrix vector multiplication, right? So this down here will be step 4 continued. In fact, let me zoom in just so my marker appears a bit bigger. So to compute xg, right? One way we can do is we can simply just do this multiplication up here, right? So we have each of the individual shape functions evaluated at the Gauss points. We have all of the x coordinates of all the vertices. We have those as well, right? So we can just brute force that calculation, or we can make use of basically like a dot product, okay? So one way we can do this is that we can do x1, x2, x3, x4, right? So essentially store all of the x coordinates from our vertices into a vector. And then we're going to multiply that. We're going to multiply that by our shape function derivatives that we computed or excuse me, the shape function values that we computed from step 2. Right? So this is n1, n2, n3, and 4. So this right here is step 2 in vector form. Okay. All right, and so in my algorithm here, you're going to see that I'm putting things in matrix form and vector form pretty often, right? And so that is a good hint, right? And so you should definitely do that for your final project as well. Just because MATLAB handles vector multiplication, matrix vector multiplication, matrix multiplication, that's very easy to do with MATLAB. Okay, it makes your code very easy to kind of interpret as well. Okay, so the more you can kind of put things into matrices and vectors, the more clean your code is going to look. It's going to look more like the output here as well. Okay. Okay, so that's for XG, and then you're going to do the same thing for YG as well. So YG is equal to Y1, Y2, Y3, Y4 multiplied by our vector of shape function values, N1, N2, N3, and okay, so I definitely recommend doing it this way, especially given what the next step is as well. Okay. Okay. But then with this, you'll get a value, you'll get actual values for xg and yg, which is the corresponding physical coordinates of this Gauss point. Okay, so that's step 4. Next, we come to step 5, and so step 5 is probably the most comprehensive. This is the one we're going to do the most calculations. Okay. Okay, step 5 here, we're going to compute our Jacobian, and we're going to compute its determinant and inverse as well. Right. So remember, we need the determinant of the Jacobian. That is essentially our conversion factor between our isoparametric integral and our physical integral, right? So that accounts for the changing domain size. And we need the inverse Jacobian to compute our shape function derivatives. Okay. Okay. All right. So for the Jacobian, we are going to do a matrix multiplication. Okay. So these two matrices we're going to multiply together. This was also listed earlier in the notes, but let's repeat it here just to make it easier. Okay. So first thing is we have a matrix of all of our shape function derivatives. Right. So we have partial n1, partial epsilon, partial n2, partial epsilon, partial n3, partial epsilon, partial n4, partial epsilon. Okay. All the same shape functions, but with respect to eta. Okay. So this right here is a matrix of our shape function derivatives. Okay. So just to refresh your memory, even though this looks like a lot of derivatives, we've already computed these. So this is what we computed in step 3. Okay. And then we're going to multiply that by a matrix of our of the physical coordinates of the vertices of our element. So it would help, if in the previous part you already have vectors that define the x and y coordinates of each of the nodes of this element, right? You can just kind of put them together here into one matrix and just perform this multiplication. So x1, x2, x3, x4, y1, y2, y3, y4. Okay. So for step 5 right here, I would say that doing the matrix multiplication is almost required. Okay. You can do this by hand. You can compute each of these entries individually. So when you do this matrix multiplication, you're going to end up with just a humble 2x2 matrix. So technically you can compute all 4 entries of that 2x2 by hand and put those in the code. But I would recommend doing the matrix multiplication. It's just a lot cleaner. Okay. Okay. And so this is going to give us our Jacobian matrix, right? which, if you recall, is basically partial x, partial epsilon, partial x, partial eta, partial y, partial epsilon. I said epsilon, but I wrote eta. And then partial y, partial eta. Okay. So this looks like a lot, but if you set everything up well up until this point, you basically store everything in terms of a matrix. This step is actually very fast. It's just when you write it down on paper, it's just a lot of stuff to write down, right? But granted that you already have a matrix of your shape function derivatives, you compute that in step 3. You already have your matrix of your physical coordinates. You do that in step 4. This is just you're just kind of marrying the two, right? And so you just basically just say kiss, and then now you have a Jacobian. Okay. Okay. All right, but the Jacobian by itself is not particularly useful, but right, nice thing is that in MATLAB we have a lot of built-in functions to kind of help us out in these situations. Okay, so next you're going to use built-in functions. Okay. So first you're going to compute the determinant of the Jacobian. Okay. Right, so there's this very simple MATLAB function to take the determinant of a matrix. Okay. Or you can compute it manually, right? And so, but I would say if MATLAB gives you the function, just use it. Okay. And you can also compute the inverse of the Jacobian as well. So I believe the MATLAB function for this is I and V. Okay. So you can use the I and V function together with the Jacobian matrix you just computed. I and V will compute the inverse. Okay. Okay, good. All right, so step 5 is all about the Jacobian. So, basically computing everything, and we're going to use the Jacobian in the next few steps. Okay. All right, any questions on this? Okay, good. All right, so then now we come to step 6. Okay. So in step 6, we are going to compute the shape function derivatives in the physical space. Okay. Now this step here is also going to look like a lot of math, but if you have the matrices set up beforehand, this step is actually very fast as well. Okay. So in this particular step here, we're aiming to compute the derivatives of all of our shape functions, right? So for this example here, we have 4 shape functions because we have a quadrilateral. For your triangle, you only have 3 shape functions. Okay, so you have partial n1, partial x, partial n2, partial x, partial n3, partial x. Okay, partial n1, partial y, partial n2, partial y, partial n3, partial y. Okay. So this is just going to be the multiplication of 2 matrices here. Okay. I'm not going to write them all down, just because it's a bit tedious. Okay. But I will tell you, which steps that we computed. Okay. So the first matrix that we're going to multiply here is the Jacobian inverse. And so we just computed this. So this is from step 5. And then next we have our matrix of our shape function derivatives in the isoparametric space. Okay. And this one we've also computed. This was from step 3. Okay. Right. So if you're following along in the notes, so step 6 looks quite complicated because it's the multiplication of several of these two huge matrices, but we've already computed them. And so you just have to kind of multiply those two together. And then voila, you have your shape function derivatives in the physical space. Okay. Okay. So one little thing of notation here, you'll see this in the code and you'll see this in the notes. So this matrix here is actually, quite key. So this is something that you will reference later on. We call this matrix BG. Okay. All right. So we're going to utilize BG to compute our element stiffness matrix. Okay, so that's step 6. So step 6 looks scary, but it's just, you're multiplying two matrices that you have already. So it's just literally one line. Okay, step 7. So step 7 is something that you're only going to do in part 2 of the final project. And I guess technically part 3 as well. So for part 1 of the code, you don't have to do this. And so step 7 here, we're going to compute our heat source or thermal generation term at this Gauss point. Okay. So we're going to compute SG, which is simply our thermal generation function evaluated at xg, comma, yg. Okay. Okay. So of course, this is problem dependent. It's going to depend on the functional form of your thermal generation function, but we've already computed xg and yg. These were computed in step 4. Right. So I'm trying my best, to as we go through the steps, the algorithm, any algorithm I think looks intimidating. It's a lot of mathematical steps, but it's important whenever you see an algorithm to see that everything kind of progresses in kind of a logical manner. And so things that you're going to need later on, you probably already computed them in an earlier step, right? And so when you're trying to read this algorithm and kind of make heads or tails of that, that's something that you have to kind of remember. Okay. And at that point, step 8. And so in step 8, we've kind of computed everything that we need to already. Okay. So in step 8, we're just going to basically add those contributions to our element stiffness matrix and element forcing vector. So we're going to add the contributions from this Gauss point. Okay. Okay. So with this one, we're going to make use of our update notation that we've used, many, many times in our previous codes. Okay. Okay, so for the element stiffness matrix, we're going to say element stiffness matrix is equal to element stiffness matrix plus the contributions from this particular Gauss point. Okay. All right, so this is going to be KE is equal to KE plus. We have BG transpose multiplied by K, where K is our thermal conductivity, multiplied by BG times the determinant of our Jacobian multiplied by our Gauss weight. Okay. Right. So again, looks complicated, but we have all of these things here. Okay, so our BGs, remember we just computed these in step 6. Okay. So step 6, remember we computed the shape function derivatives in the physical space. Okay. our determinant of the Jacobian, we computed this in step 5. Okay. K here is our thermal conductivity, so that depends on the problem. So this is just a problem parameter. And the Gauss weight also is a parameter for this particular problem. Okay. So that's the contribution to the element stiffness matrix, right? So that is basically our contribution from our shape function derivative term. Okay. Next, we have the contribution to our element forcing vector. So again, this is only in part 2 and 3, right? So you're not going to do this in part 1, right? So for those of you still on part 1. Okay, so FE is equal to FE plus we have our vector of shape functions of values transposed multiplied by our thermal generation term times the determinant of the Jacobian multiplied by our weight. Okay. Okay. Where NG here, this is something we already computed. This was in step 2. Okay. SG, we just computed this, so this was step 7. Okay. Right. Determinant of the Jacobian, just like above here, this is from step 5. Okay. And the Gauss weight, of course, this is a parameter of the problem, a parameter of the Gauss scheme that we chose. Okay, so again, looks intimidating, but these are all things that we've computed already. Hopefully they're already in matrix form or vector form, and so we just have to just multiply them together, add it to our element stiffness matrix and element forcing vector. Okay. Okay. Good. All right. Any questions on this before we jump into an example? Okay. So technically, there's one more step after this, which is actually in a separate loop, and so you can call that, step 10, although that wouldn't actually be appropriate, or I guess step 9, just because we usually do this in another loop, but you also need another loop to do the Neumann boundary conditions as well. But I think it'll be more appropriate to talk about that when we're reviewing our project specs. Okay, so when we're reviewing the project document, we'll discuss the Neumann boundary conditions because it is, like I said, and so of course this is part 3 of the problem. Right. So like I said, part 3 is the most tricky, not because Neumann boundary conditions are complicated. It's more in the programming in terms of, how do you determine which edge is on that Neumann boundary. Okay. Okay, so with that, let's do an example, right? And so just for the sake of time, I'm not going to write it down. So I do want to make sure I have at least 30 minutes to go around and just help people with their code. So let me go ahead and open up our lecture notes here. Okay. So these are the lecture notes that are posted online. This is lecture notes 12, right? And if you go near the end, there is an example of me kind of implementing this exact algorithm, okay? Just so that you can kind of see it in action. And so, on the one hand, the pseudocode that we just went over, it's written in a way where you can just implement that directly in code. But I think it is still useful to kind of look at an example worked out, just so that you can kind of see all the calculations in action. Right? Okay, so for this example here, we have the following element, right? And so this is the element in the physical domain, right? So you can see it has kind of a trapezoidal shape. This is not an element in the isoparametric domain because it's not a perfect square, right? So this is a great example of an element that you might see in something like the final project, okay? So for this element here, we're given the coordinates of all of the nodes, right? So node 1 in the bottom left, that's at the origin 0, 0. Node 2 is at 1, 0.2. Node 3 is at 0.8, 1. And node 4 is at 0.2, 0.9. Okay? In this case, we do have a thermal generation term. So our thermal generation term is S of x and y. That's 20x plus 10y. Okay? And in this case, we also have a Neumann boundary condition as well, but I will kind of save that discussion for when we go over the project specs. Okay. Okay. So what we want to do in this case is we want to go through our isoparametric algorithm. So basically steps 1 through 8 on this element here, just so you can kind of see it in action. Okay. All right. So first step is we're going to choose a Gauss point, right? So remember the Gauss point is a point that's in your original, not in the original, sorry, that's in your isoparametric element. Okay. And so this is governed by the Gauss scheme that you're choosing. And so for a 4-node quadrilateral, right, one of our Gauss points is -1/√3, -1/√3. Okay. Okay, step 2. Step 2, we're to compute our shape function values, right? So this is NG. Right, so N1G, N2G, N3G, N4G. All right. So our shape function here has particular expressions. Okay. All right. So for instance, right, N1 is equal to 1/4, 1 minus epsilon, 1 minus eta. Okay. So essentially, all we're doing is we're just plugging in for our epsilon and eta based on the Gauss point that we chose. Okay, so that's what you see in this step right here. So we're doing that for n1, n2, n3, and 4. Right. So keep in mind all of the shape functions have different expressions. Okay, that's why we get different values for all 4 of these. Okay? All right, step 3 is that now that we have our shape function values and we've already established the coordinates of our Gauss point. We're going to compute our shape function derivatives, okay? And remember, we have analytical expressions for all of these shape function derivatives. Now, in your project, your shape function derivatives are going to be much simpler, right? You'll see very soon when we go over the triangular element. But, we need to compute all of our derivatives here, okay? Okay, step 4, once we have all of our shape function derivatives computed, right, now we can actually start using these quantities. So step 4 is to compute the physical coordinates of this Gauss point. Right, so that was kind of the first step that we talked about today. So we're taking n1 times x1, x2, n2, n3, x3, and 4, x4, right? Multiplying them together and adding it through, okay? So just like we talked about today, all of our shape functions here, this was computed in step 2, okay? And then all of our nodal values, x1 through 4, y1 through 4, that's read off straight from the mesh. Okay, step 5 is to compute the Jacobians. And so remember, this is a lot of math, but all this we've set up already. Okay. First, we have the shape function derivatives in the isoparametric space or the parent domain. This was in step 3. Okay. These nodal coordinates are read off the mesh. Right, so we just have a very simple matrix multiplication. We let the code handle it for us. We just have to set up these matrices. Okay, and so we get some value there. Right, so this is what we get for the Jacobian. Okay, so we get this 2x2 matrix for the Jacobian. Okay, and then from the Jacobian we can compute its determinant. We just use a simple MATLAB function for that. And we have its inverse as well, right? So both of those we use MATLAB functions, right? So we don't bother computing those by hand, okay? Okay, all right, step 6. Step 6, we're going to compute our BGs, right? Our BGs are our shape functions in the physical space, right? So if you remember just from, maybe like 20 minutes ago, we're just multiplying our Jacobian inverse, okay? So this is our Jacobian inverse from step 5. Next, we have our matrix here of shape function derivatives. This was in step 3. Okay. We're just multiplying those two together, getting our shape function derivatives in the physical space. Okay. which is this one right here. Okay. Step 7. So step 7, remember, this is where we compute our thermal generation term. So in this particular problem, we do have thermal generation. If you're working on part 1 of the project, you're not going to have thermal generation, but it's good to see how this works. Okay. So our thermal generation function was just 20x plus 10y, right? We're going to plug in our physical coordinates of our Gauss point that we computed in step 4. Right, and so we just have 20 times that plus 10 times yg. Okay. All right, and then step 8, we're just going to put it all together. Okay, so step 8, we're just adding our contributions to our element stiffness matrix and our element forcing vector. Okay, so step 8 is kind of a, I didn't write anything down for step 8 just because it's we've kind of already written it down, but just make sure that you actually save those contributions, okay? Because you did a lot of hard work kind of saving these, and so you want to make sure that you save them out. Okay. All right, so I know I went through that pretty fast, but I mostly just wanted to make you aware that this example does exist in the notes, and so you can refer to this to see how the algorithm's done. Okay, so just kind of running through the calculations yourself, seeing if you recreate the same things as me, I think will help you kind of with the code and with the understanding of this algorithm. Okay. Okay. Any questions on this example here? Okay. All right, so last thing I want to go over in the notes before we just quickly review our project specs is the isoparametric triangle, okay? So this is exactly the element that you're going to use for the project, okay? Now, the nice thing about this is that the shape functions are actually very simple, right? So n1 is just epsilon, n2 is just eta, and then n3 is 1 minus epsilon minus eta, okay? Now, the nice thing about these shape functions here is that they're all purely linear. Okay. So we don't have any cross term here that we need to worry about. And so that means when you take their derivatives, right? So remember, that's what you're going to do in step 3 of the algorithm. The derivatives of a linear function is just constant. Okay. And that's no accident, although it is very nice, right? And so when you compute your shape function derivatives, they're actually very, very simple. And so I think in the previous example, there was a lot we need to plug in for. For a triangle, we don't need to do that. Okay. Okay, so besides that, the rest of the algorithm progresses kind of in the same way. Okay. But one thing you do need to know for the triangle is you do need to know its Gauss rules. Okay. So I did get a couple emails on this over the weekend, just because we didn't go over Gauss quadrature on a triangle, but it's fairly straightforward, right? And so it's basically the same method. It's just you're going to adjust the coordinates of the Gauss points as well as the weights. Okay? And so I believe in the project, I'm having you do a 3-point rule, which is that one right there. Okay. So for the 3-point rule, all the weights are 1/3. Okay. So that kind of makes things simple. And then each of your coordinates are the following. So the first Gauss point is 2/3, 1/6. Second Gauss point is 1/6, 2/3. And then the third Gauss point is 1/6, 1/6. Okay. Okay, so make sure you're referring to this when you're doing your Gauss quadrature. Okay. You may not need this explicitly in part 1. So remember, in part 1, you can technically do without the Gauss quadrature, but you are going to need this in part 2 for sure. All right, any questions on this? Okay, all right, so let's go ahead and let's review the project specs just really quickly, just so that everyone is kind of on the same page in terms of what you need to do for the project. Okay. Okay. All right, so again, I think we went over this, maybe a little bit less than a month ago, but, we're just going to kind of go through it again one more time. All right, so the whole point of the final project is, this whole class is all about, theory and the math and the algorithms behind finite elements, right? And so you can see this project is kind of the culminating experience for everything that we learned in this class, right? So the whole goal of this final project is to write your own finite element code, right? Admittedly, we are going to be leaning a lot on some packages within MATLAB to kind of simplify some of the more tedious steps for us. But there's enough here for you to kind of demonstrate that all the algorithms and all the theoretical understanding that we've learned throughout the class, you can implement that to solve code. Okay, right? And the domain for the code is just going to be the simple L block. Okay. Okay. All right, and so the other part of the code here, just like we just mentioned, is you're going to be using isoparametric elements, and you're going to be doing that on a triangle, just because the mesh that MATLAB creates is a triangular mesh. Okay, so all the elements are perfect triangles. Okay, okay, and so the project is split into multiple different parts, right? So part one, part two, part three, part four. Okay. So part one of the project is you're going to write just the simplest code that you can to solve a finite element problem, right? So part one, we're just going to do simple diffusion with Dirichlet boundary conditions. This is kind of the bare minimum of what you need to get a functioning code. Okay. Okay, and so in terms of the amount of code that you're going to write, part one is probably the longest. But at the same time, a lot of the algorithms or a lot of the code that you need to write in part one, we've kind of gone over together in class. Okay. Okay. All right. And so, I would definitely read these specifications here just because a lot of the data structures that I provide for you, they do take a little bit of explanation. And so basically using the nodes vector, the connectivity matrix, all the different kind of, scalar variables, the number of nodes, number of elements. And so make sure you kind of read through this to kind of make sure you know how to actually use them for the project. Okay. Okay. Part two, you're going to basically just augment your part one code to include thermal generation. Okay. So part two actually doesn't require that much code compared to part one. Part two is actually quite short. And so if you can do part one, part two is pretty straightforward. In fact, if you're following the algorithm exactly as I discussed, right? Some people do that just for part one, just because they're following the algorithm. So you may just complete part two just by mistake. And so that's fine. That's fine as well. Okay. Okay, part three. Part three, I think, is going to be the part that I think most people struggle with because this is where we need to implement the Neumann boundary conditions. Okay. Now, the Neumann boundary conditions themselves are not that difficult to understand, right? So we kind of work with them a lot, but it's just the way that you have to actually implement them that's going to be challenging. Okay. Okay. And it's challenging from this perspective because, right? Right. So let's say that you have your domain here, right? Right. So this is kind of broken up into the different elements here, right? Right. So what's challenging about the Neumann boundary conditions is that not every element here borders a Neumann boundary. Okay. So first of all, there's a bunch of elements that don't border any boundary at all, right? So we have a lot of interior elements that are just interior, right? And so we have to filter those out. So we have to filter basically every element that does not touch a boundary. And then we also have elements, right? We also have elements that border a boundary, but maybe they border a Dirichlet boundary, right? So we have basically edges here. Maybe these are Dirichlet boundaries. Okay. So we need to filter those out, right? So we need to basically, only consider elements that border our Neumann boundary. Okay. Right. But that's not the hardest part. The hardest part is that, for the elements that do border the boundary, right? As in this figure right here, right? So let's say we're looking at element 96 here, right? So for this element here, right, we have triangles, we have three sides, but only one edge of this element out of three is comprised of the Neumann boundary. Okay. And the reason that's relevant is that, in 2D, right, in order to incorporate the Neumann boundary, we're going to perform a line integral only on the edge that borders the Neumann boundary. Okay. All right. And so that line integral, you're also going to do Gauss quadrature on that. And so for that, you're going to do a 1D Gauss quadrature. Okay. Okay. But that's not the hardest part of the algorithm. The hardest part of the algorithm is, first of all, finding the elements that border the Neumann boundary, right? So there are functions that help you with that. But once you do find the element, is you have to determine which of the three edges you want to perform the line integral on. Okay. Okay. All right, and so in the specifications, I do give some explanation for this, and so it is quite long, but please do read all of it. Okay. And so I do create, I have also created a lot of data structures and vectors within the code itself to help you. But that is something that you need to kind of determine on your own. Okay. So at the very least, I would if you haven't started on the code yet, I would definitely try to get through part one, part two this week, because I think part three is going to take you a while to kind of figure out. Okay. And if you can get it done before Thursday, that would be ideal, just so you can ask me questions next Thursday. But on this Thursday, but I'll also be available next week as well. Okay. Okay. All right. Any questions on this? Okay. All right. So that's the main coding part. And so I think there's one more part here where you're to apply this to your own geometry. So I know some of you have already kind of started playing with this, which is kind of cool. Okay. Right, so I think we went over this in detail last time, and so just make sure that you know that you're creating a geometry for the first letter of your last name and the first number of your campus-wide ID. Right, and then for the bonus, you can also improve the efficiency of the code. Okay. Now for the bonus, I will give a very minor amount of extra credit on this. I don't know if I've written here how much extra credit. Um, But usually my plan is I think the project is out of 100. And so if you do improve, if you implement every improvement on efficiency, I'll give you up to 10 points. Well, I have it right here, 10 points of extra credit. Okay. Now I won't give you any hints on this, right? And so it's extra credit. And so, it's not something I can help you with because it's not a requirement for the class. But if you do improve the code, right? And you do kind of explain it in your report, and I see it in your code, right? I can give you up to 10, but I'm not going to give you any hints on this at all. Okay, so this is something you have to kind of figure out okay. Okay. All right, and then the rest of the specifications here just describe the figures that you need, the components of the final report, and that this is also an individual project. Okay. All right. But for now, I would say, I wouldn't focus on the report just now. I would just focus on trying to get all three parts of the code working as quickly as possible. Once you have all three parts of the code written, you can then implement part four. Part four is kind of more of a fun thing. And then you can start writing your report after that. Okay. But priority number one is try to get the code working. Okay. And try to get it done, while you still have me available because outside of my office hours and outside of lecture on Thursday, I'll try my best to answer you guys' emails to kind of look through your code. But we're quickly running out of time for us to actually kind of meet together, right? So you want to make use of that time as much as possible. Okay? So the deadline for the project for everything for the code and for the final report, remember, is Sunday, May 17th, and so that is the Sunday after finals week. That's not this Sunday, that's the following Sunday. And so that deadline will come up to you very quickly, especially if you have a lot of things going on these next couple of weeks. Okay. All right. And so that took a little bit longer than I wanted to. And so we still have about 25 more minutes. And so for the rest of class today, if you have your code, if you have questions, I know a couple of people already kind of wanted to talk to me. And so I'll be going around for the rest of class today and helping you guys with your code. If you don't have any questions today, or if you're just kind of just going along, you are free to go. And then Thursday is just going to be all just project workshop. Okay. All right. Any final questions before I start making my rounds? Okay, all right. So I will start making my rounds. If you have questions on Zoom, just go ahead and drop something in the chat. I will go ahead and try to come back to Zoom when I'm done making one round around the class. But generally, I do prioritize the people in the class. And so if you do want help on your project, try to come here on Thursday, and then that'll kind of help you get seen faster. Okay. All right, but then, if you haven't picked up your exam yet, I did bring the exams. Today will be the last day I bring them. So please pick it up. If you don't pick it up today, it'll be in my office. Okay. All right, so if you have questions, just raise your hand. I will come around to you. Oh, okay. So that right there, so that's normal. Sorry, I just but one of the points here, so figure 4 is created automatically. So it looks like a black hole. Yeah, like I get it. Right. So you'll see that these are just all the living similar. Right. So this is something. This is just created for your own. It's just for your own. If you want to see it a bit more clearly, you can increase the element size here. What your tablet?
Oh, it's because you also have like your own separate.
What create one?
This takes like 30 watts for like fast charging. The laptop's like 50.
That's 80.
Like the headphone case. 5. It's like it's the next one.
Okay. Yeah, I think for some reason that error is that can just close all the.
Get it? What?
Yeah. Okay. So you can see now, so these are just the labels for the
30%.
So these get created no matter what. You can turn them off.
For you?
Yes, on 21.
Oh, I thought that was the night before.
But these are just. I know in case I want to do things. So let's say that you're going to check right.
Oh, I feel like I can run too. Because when I open it, because all kids have to use.
So the 120.
This one's from
You can see
2014.
from this matrix here that element 1 has nodes 48, node 30.
I have the glue and
go ahead and
Back with
yeah.
element 1 right away is this element right here, right? And so connectivity,
Yeah.
one of these nodes is 48, one of these nodes is the other plus.
Oh, it's the weight.
yeah.
So I thought you meant like on this.
So you see that that's also.
Oh, is that
So I'm gonna put here, this is node 48, this is node 30.
I was like,
Exactly what this is in the yeah, so figures 1 through 4.
now I realize.
I mean, 1 is just like a turbo mesh.
But
But then 3 and 4 there, that's just to kind of help you better understand
Under
this scene.
So there's some. But we can get straight. So the instead of we said it's that's so
Exactly. Yeah, so try to make use, so I know, I think in the previous codes we used pause for the positions. But for this one, the name of the position vector is actually node. So if you open up the nodes matrix there. No, it's not. Okay, so these are the coordinates of all the nodes in your mesh. So node 1 have coordinates minus. Yeah, so in your code here, you're gonna make use of not the positive, because positive is that put the arrows. You're gonna make use of them. Yeah, so try to
oh
so in this one, exactly, okay. Yeah, so remember you want to retrieve the x coordinate for this particular Gauss. Yeah, or excuse me, the physical coordinates for this particular element. Okay. Yeah, so we'll give that a try. I'll make my round. I'll yeah. Yeah.
When up the instruction, it says to see down.
Yeah.
And it says when you fresh on.
Yeah, you can do that. So I was just on David here. So there's 4 plots that actually show up. So figure 1, figure 2, figure 3, figure 4. So these are not solution plots here. These are just to kind of help you kind of visualize what's going on. But if you try running the code,
I see.
This one I modified, I've been typing stuff in it, but this one has been completely unmodified.
Yeah.
Because the one you gave us confused me.
still on 120. Oh, okay. Yeah, it's because okay, yeah, so this error is because okay, so I apologize. So I think in the older versions of MATLAB, kind of ignores these and kind of just randomly of it. We can just put we can just comment this out there. Yeah, that was my bad. I didn't know that the there you go.
Okay.
Yeah, so that was my bad. So I'll change that in the starter code because that line of code I used dot dot dot. So dot 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 is actually a special character in MATLAB. And so that's why it was complaining about that. But I mean, you'll implement that later. But I think if we want to just run the code first, we can just run.
Okay.
Yeah.
And then just make sure I'm understood correctly. So, this. For this part,
Mhm.
we're using the ones from
Exactly.
the notes, right?
Exactly. Yeah. So the ones that we just went over.
Okay,
Yeah.
and then just in the same order that they're listed, one through like 4, or is it in the order of like these? Or points? Because I just wrote them for one. Here's one.
Yeah,
two.
so right. So these are the Gauss points for every for a particular element. And so that's actually independent of these
Okay.
here. So if you want to keep it simple, you can just keep it in the same order as in. Although technically you can do them in any order, but just do it in the same order.
Okay.
Yeah.
Thank you.
Mhm. Yeah. Okay. Yeah, we need these generics. So the part was good from that sort of so this we can now. Oh, it's okay.
So it makes code density. So what I did in the other parts.
Yeah.
According to the parts.
Yeah.
I have moved everything.
Oh, yeah, that's fine.
I'm looking for connection.
Yeah.
Completely.
Yeah.
Instead of going for it, so I put the 6 papers.
Yeah.
So I'm doing only 2.
Oh, yeah, so that's fine, yeah, so figures 1 through 4, you only need those at the beginning. But then you don't need the required.
It was like I'm using asking sponsors like
Yeah.
so if I many times for wait before I work. Just like in my custom mode maker of my serial state, so it's really like this one.
Yep.
So outer mounting or like.
Yep.
But for that thing when I try to like key, it's like doing like this one. This one. And like this one.
Oh,
So
interesting.
what I did. Yeah, it's like it's not showing that it's what I did it here. Here solution. I use like 3 different. So people like writing this one,
Yeah.
this one, this and then this combined by the
Okay, yeah, that's fine.
but I use for the 8 thing.
Yeah,
The same you with the top like the outer area
yeah,
and the small areas.
okay, yeah,
But it's pretty hard for K because you cannot like if you stand the boundary like this one. So it's pretty hard. I've tried but it's going like this one.
I see.
Like this area, this area.
Oh, I see.
It's been like shown like inverted K.
Oh, I see. Yeah, no, that's perfectly fine. That's actually very smart. So, yeah, well, that's.
But meanwhile, like you said in the class, like you more gonna talk about the extra credit thing.
Yeah.
I have like made something on the that point.
Okay, yeah, I would just implement it and then I'll flip check that.
Extra credits in the The project or?
Yes.
Or on the paper or on?
Just on the fly.
So I can like, that means okay, only in the part. There's only in the part, complete 6 period, you will mention of you. Let's solve the nominated.
Yes.
So
Yep.
that's okay for the part B and part C, only the two zero.
Sure. Yep. Yep. That's perfect.
Even like in the first part.
Yeah, yeah, so that's something that's interesting here. So the error is coming up because if you look at these corners.
Starts from, you see here,
Yes,
and get and what is the, but I have covered this thing in the part C. Looks, that's probably the generation of us things. That thing is covered.
oh, okay,
But what you do is, or should I be doing that?
for part A. Yeah, so that one actually is it's interesting, so if we kind of go to, yeah.
Yes, fine.
So the error for this one is actually originating from this corner. Look at this corner, this corner. So this corner technically is part of this edge, it's part of this edge, the same magnitude.
So,
Yeah, so the issue is because this particular location is part of two edges, you know, technically there's two boundary motion. Exactly, so in the reference solution, the way it applies the boundary, it does it in a certain order. But, you know, depending on how you go through the code.
one is not followed.
Exactly, so you can modify that if you want, so you can modify your code to be the same order as this one.
Or then you can write in the solution that this is happening because of this one.
Exactly, yeah, yeah. So that's totally fine. So this is actually something I expect. So actually in my solution too, I have that discrepancy.
Can you try it, but it's like same thing on any other solver like Python solver and Python solver.
Yeah, you're gonna get the same thing because it depends on the order in terms of when this node is visible. So you can see in your code here, it looks like it applied the blue boundary condition, right? But in the reference solution, it applied the high boundary condition. And so it looks like a big difference, and so I think especially here, it kind of looks big here, but that's
Example, this one.
exactly. So it's originating just from the fact, just from this one. So that's where it's all coming. Okay, yeah, no, I think that's fine. I mean, you have a mesh, that's the good for.
I have like. But this something was all into the ratio.
Yeah.
Is there any like research paper? Yeah, about because
It's up to you.
it's like I didn't try.
Yeah, it's whatever you want. This is more just the fun part. So there's no yeah, it's basically, you know, I've given this project in the past, but it's a little bit anticlimactic that you only apply everything on the same geometry. And so I wanted to give you guys a chance that you write if you wrote this code, you can apply it to any geometry. Yeah.
But we have a both. First is the
Yeah.
then we have
Yeah.
So if someone did the extra if it comes on the outside, yes. Or at the end, because in the methodology, there is a definition of the equation text. But if like for Kesta, a vivid code, it's like a methodology or a text exactly applied. So can we write a small paragraph in a methodology or this explain and because
I think you can just explain the results and things like that. So I would exactly, yeah. So you can create like a subsection within the results, say like optimized code. You kind of explain. Yep. So. Okay.
Usually, in here. Yes. Find location.
Yeah. Yeah, so 1 and 7 have conditions of 100, yep. And then 3, 4, 5, 6 have 75, yep. And then 2 and 10. Yep, taken over.
Yeah.
All right.
I'm not dead right now. I'm not going. I can't look at that.
Exactly. So your GP matrix here, right now it's empty.
Have
So
you
I
ever
have created
taken
a
or do you know
matrix for it,
anybody that's
but I haven't assigned a value for it.
There's this. Did you get an email about them?
That's based on kind of what we discussed in this.
There's 2 classes we had.
No, so actually
biofluid
no,
course.
let me bring it
And I
up.
wanted to ask you to see who's, if you've taken or you know some body fluids.
Who, for that class, they're here, it's pretty.
Yeah.
Combustion, it was wet, but I don't think he's.
He's not coming back.
That's what everybody was saying. He's gone.
Like from the university.
Yeah.
Oh, where did you?
Nobody knows.
Yeah. The rumor is he's in. Oh, okay. Oh,
Yeah, yeah. So
He helps like.
So the first Gauss point is 2/3 minus the second Gauss point is 1/6 thirds.
But yeah.
So that's where you kind of list
Yeah,
it.
he's a friend.
Just because you're
If that's-
gonna be
if that's the
like
thing.
so many
Yeah,
times.
so he's
So
got
basically just kind of pre-defining it at the beginning.
Is you bro?
So that we can kind of make use of it later.
Yeah, so
This is also very traditional. Like,
Yeah.
you know, I know in the project, I'm just having you do one Gauss configuration. But the way this is written here, technically you can change it.
Okay, so I'll
And so-
take
If you want to do
That
a full one
file
Gauss,
sounded.
all you have to do is just change up here and the rest is for
People
code.
say has last,
So it's like.
has like minor is first year.
I'm sick.
It's like old discussion because it's more research
Yeah.
oriented than
Okay.
like here's your test, here's this.
Yeah.
But it's like, hey, we're sitting down, we're discussing what we.
The next to do is each.
And going through.
Exactly. So this part of the code.
Okay.
We're sitting here taking like.
Technically the isoparametric.
It's for discussing.
Gotcha, okay.
I don't know.
That's what maybe like step 1, step 2.
Because it was the first time about this time.
That's for this.
But-
Oh, was it like an experimental course?
Yeah, it wasn't. But it was breaking.
Oh,
For assembly candidate, but because the assembly should be very similar to how the assembly previous codes.
His work.
If you look at our frame value, you look at our 1D.
Oh,
That's
okay.
Just for research.
Gotcha. Okay.
So that's the element stiffness matrix. So the assembly is this part of it.
I'll
So
have to
see,
work
we can
out
do the
the
assembly very
myself.
elegantly, so you can.
Because
you know,
I think it's
there's
at
a way
4,
for this.
So
Within just
I
a few
would
lines.
probably need.
But I do it kind of like, I do kind of
Yeah.
brute force just because I think it's nicer this way. But yeah, this is the kind of the same.
Actually, if someone invites to the biofluids,
This one is the steps.
and see who. Got paid in class on this because to my buddies that he's specific.
Yeah, I like
to rich foods. So combustion.
That one also is very similar to the previous one, except you do need to make use of some of these special mesh files. Yeah, so I do that for you, so
It's that guy.
where you make use of
What
it,
is
find those function. Remember, the way that we apply derivative boundary condition for every node that
There is
we're
one
in,
for that Mad Hat.
we're changing the
If you want
matrix.
to
So
do
we're
fluid
making the
Yeah.
making the
You
row
want
all
to take
zero,
fluids
except for
classes,
one. And then
Okay.
super
and then the
knowledgeable,
derivative
really nice
values would
and everything. Like you never have to come to us.
So that's essentially what we're doing here.
Everything's
This
on
line nodes function will tell you.
So he's another
exactly
Habib.
which nodes.
Quizzes, tests, everything, submit on.
Oh, okay.
His quizzes are like really loose. Because you have a week to do your homework.
Yeah.
And he gives you everything for it.
Yeah, so everything down to that is
His quizzes, And the quizzes is where people lose points.
Yeah.
Because he's like, okay, here's a problem. You have 15 minutes to do it, and it's minutes.
So part two is you're actually gonna be,
And
you're actually gonna be
adding
adding
like a group.
part two is,
But like
um,
my buddies that took him
yeah,
this
so part two,
he
there's
didn't
gonna
get
be
right taking doing any quizzes.
You're both in one.
I'm
gonna add- so-
other
so you're-
classes they took.
The assembly's gonna be exactly the same.
Quizzes are why I got classes
Here.
7 days.
You are gonna modify the construction of the elements.
Really
But now,
like, not
both
easy,
with
but
one generation.
easy to do well.
Then part 3 is.
Alignment boundary conditions. Yeah.
Okay.
One step at a time. Do part one, part two first. I think those are very good feedback. This week, and then part three.
I'm
part
thinking
three-
updated. It's
I worked on the other class.
I know. The CFP project. Yeah.
The
Well, the good news is the CFP, once you have it set up, you can just kind of run it in the background, I guess, but.
they need to try to iron this out for I forget.
Has NASA actually been involved?
Yeah, for sure.
they started last year. They have
Yeah.
the Spark Center. It's a aerospace group.
Okay.
That's with from NASA.
So we're using the ones for the triangles, so we're using these ones. Yeah, these ones right here. Yeah, so the triangle has different statements. So the algorithm we went over in class, that was for the quadrilateral. But for the triangle there, these are. Wait. Yes, yeah, but instead of, so these shape functions are for the quadrilateral, so you're gonna replace the first of those.
Oh, this makes more sense now.
This.
Because a few weeks ago, maybe even now a month and a half ago, maybe even two, there was an email that was sent about
Yeah, we do.
about research with Clemson students, and now this makes sense because here it says
One minus 2/3. And that's a.
Wayne
Yes.
also
Yeah, but then when
said
you go
that in
to the next
addition to
chapter,
research being
Yeah.
research being performed under the support of this grant will be in collaboration with the University of Washington and Clemson University.
Second iteration. Regular ones?
No, and
Third
Washington.
iteration, actual ones.
But
Yeah,
and I
that's why
remember-
we look at the
I
score.
remember
There's a.
wanting to go for it,
So
but I
first
think
iteration of the
they
loop
request
would
like I would have to leave, like I would have to like quit my job
Yeah.
to do
be-
it, and I was like,
Next one.
I don't know if I want to do it.
So you wanna make sure that when you write your code here, it's flexible enough so that it can handle all three. So that's why, early on in the code, right, so this is perfect, so define the Gauss points here, make sure you make use of this G vector here. Inside this. Yeah.
Left box that equal you.
Oh, I did not see that. Usually people will leave those alone. We can go down and check after this. Oh, okay. You might check the engineering office of the E1. You can check if anyone picked it up and they lost it. Yeah. From that. Check it. Oh, yeah. Oh,
Nah, it's not. It's empty.
okay. Oh, dang. What's up?
I'm just a little concerned about the third.
Okay.
code.
That's it.
Is-
Okay.
So the computed one, it's like 260 max layer.
Yeah.
That's actually pretty
You
good.
kind of tell.
Yeah.
This is might be a little darker.
Yeah. So the pattern there, that's the value that's.
To see that
Yeah.
at least second come on.
And then for the
Grew a little bit. Spark.
air.
Yeah, where's the spark?
I was
The center?
Yeah,
It's going to be in the new building,
When you build.
the one right there, that's being built. There's
Okay.
the Spark Center is supposed to be
Yeah,
end up in it.
Wait,
think about that.
is it?
Yeah, I mean, it's, just looking at the values here.
What the hell is
Fuck it.
this?
Then,
I like how we both.
the maximum range of-
Oh, it's a night owl. Okay.
There are gonna be small
Weird.
discrepancies from the way I'm telling other people,
You can get
especially if you look at the corners.
What?
And so there's gonna be small differences, that's okay, that depends on just the.
Fashion is hard.
But.
I mean,
overall
it is,
count,
but I mean, you look like a statue.
So I would check and see, so this.
You know what it reminds me of?
So I would
You've
just check
seen
and
any-
see, remember, when you're doing.
No.
Okay,
you're
well,
doing
there's
house
like
conversion,
these statues that are
is
angels,
to make
Yeah.
big angels.
Uh-huh.
I've never actually watched that.
Make sure that.
But it's like
Just trying to make sure that kind of everything in that section, it's a little bit tricky because you're doing.
quantum locks.
It's also.
Three.
doing one decaf-
So if you're looking at it, it can't
Yeah,
move.
so you wanna make sure
It's
all the
a
ways-
statue.
They are all.
And if, so it can only exist out when people like attack you if you're not
Then,
looking at it.
when we do
That's why it
the
looks.
information,
Yeah.
like it.
Boone makes
So,
the idea of
yeah,
working with the
we have
traditional
that
fashion
where
designer
it's
for the
gonna
look
be one of
and
the
not
lights
to team
on
up
the
with her longer and
angles
partner
of the-
in Halloween.
Diagonal.
Yeah.
I think makeup
does it-
artist Mike
does it
Arena.
I'm pretty sure it matters, but like, how does the code look? I guess like, I'm just a little confused as to how it like it would know which
Okay,
is
anyways,
the one. Those
see this?
there's like arbitrary things.
At this point, it's kind of arbitrary.
This one?
So the way that the code assigns them.
No.
Oh, you mean
The one
you
that
mean
they
like the
built.
engineering
Yeah,
building?
the one
Oh.
that's being built.
Oh, okay.
And so.
I thought you meant like
It's kind of what this.
a new building, like somewhere like
Well,
No,
it's a
no,
little separated. Oh, okay, okay,
Yeah,
okay.
that's the business building.
So like, so your connectivity has three nodes.
Yes.
And so how does it know that this one is mapped to?
Yes,
this?
that's
Okay,
not-
so that's always the same.
Oh, I see.
So node one is always in the bottom.
Dude, imagine if this
right?
was all engineering, like all labs
Node
and
three is always at the-
Yeah, but no, it's fine.
Yeah, so that's always.
Yeah, isn't
the
that
way that
the
the way
art buildings?
those are numbered.
yeah.
And
But imagine if this was like all labs, like
then,
if it was like some
the
bio labs and like
connectivity is, like,
imagine
one,
some
two, and three, right?
dinos.
Yes,
So that corresponds to 1, 2, and 3.
yes.
Yeah.
Yeah.
Well, that's what this new.
And if I
one
switch
that's
it
being
like
built right now,
2 and
will be
1,
mostly-
switch it around. Well, I know I could test it, but like, would it change?
But it's
It's
gonna
more
be
because
big.
The hypotenuse is.
Like big labs?
Two.
Like the whole
So
building.
so you're
Mm.
So probably big,
And then
probably not as big as some of the.
So I was playing around with the actual numbers.
But I think they're repurposing
And,
some of those rooms right
and
now.
These are the edges of
Because it's like
particular
the
brand.
wind tunnel hasn't been. used. And that was the.
So that would be this one.
Yeah, that was.
Yeah, these three.
my
So the one,
area.
the bottom two, and then the diagonal.
So.
Yeah,
So it's like really close to.
Oh, they are.
That room.
Oh, okay.
So would you say that's where maybe my area would be coming from?
It's always hard to say. I haven't taken care of.
So.
Unless you
Oh,
want
no,
to. These are the physical portions. They're not the.
Which one?
I have an
Those
understanding,
index-
better understanding now.
Yes, those are the things.
But
Yeah, so one thing that's interesting about the MATLAB measures that looks, if you look at the elements here. They're all pretty much equilateral triangles, so they're all gonna be the same, but it's not the physical, not the physical coordinates that. It's the.
Imagine if we had dinos
When you
here.
map it, it doesn't work.
And I guess I just want to show you.
I think one of them is going to be a
We're in the
supercomputer.
Spark Lab. I just ran it up to like
Oh,
0.06.
no.
Okay.
I've heard it.
0.006.
Yeah,
And
I remember
the error did go
at the
down
time-
to like 0.18.
oh, good.
So is it anything at this point? Just like an efficiency,
percent?
maybe like an efficiency
I've heard
error on
of
your
it.
part?
But
Or is
I
it
don't
just
think I
that
ever have class.
based
Oh,
on
okay.
the formulation
Well,
of
I
the
think what
problem,
we're trying to
it's
do
gonna
is
need a
like
very
understand
high
how
mesh to
much-
be like really close.
I think
So for this particular, there's always gonna be a little bit of error,
I can't remember.
because if you go back.
It's like years ago.
So
Yeah.
if you look at the dimension right at this corner, right, so this is where you kind of see it the most.
Yeah.
right?
I feel like
So that
They
corner
kinda
right there, if you think
grow
about
this
it,
apart.
it's technically part of
For sure.
traditionally
Well,
valid.
this
Yes.
is talking about how many years old.
So if you look at that
Yeah,
one, if you look
it's
at
like
your
aerospace,
resolution,
I don't know.
yeah. I know,
That's
for
different
example,
values.
Long Beach,
And so the
they
reason
they
for
run
that
they
is that
launched a
node, when you're
biomed,
moving over
their first class.
that node is actually visited twice.
So my
Yes,
friend's
because
wife
literally when you do this one,
was part of the
so
first
depending on
class that
order,
graduated from Long Beach's
the reference solution always
biomed
does it
program.
program. But then the way that
But they would for
people
sure
typically
need
program this, their
more
code,
facilities.
and so there's always going to be.
I would
So
even argue
that's an error that's unavoidable. So
Yes.
and so it doesn't. You can refine it.
I don't know if I don't know if they have the permits or if it's even
So I wouldn't worry about that.
and also
The fact that the
financial-
code is going
financially
extra money,
to-
that's
and I don't know if it
Is
would
there
be
like
also
specific
feasible
area where you would say like?
or if it would
this
be
is, like,
even
good
worth. Because if they
So
want
I
to
actually
expand
changed
all
the
like
formula
new
to
programs,
make
they're gonna need more.
Yeah.
So I haven't
more
I haven't done a
faculty.
thorough, right, but people kind of got.
So what I would-
that
I would say is like bulldoze all of E21, like those side areas, and like
So I actually
actually
don't know. I
make
haven't
buildings where it can be multi-story. Because then you could, because like obviously the problem is that this university is constrained land-wise, so you can only build up.
Yeah, like.
So from that like 200 to 400
Replace one of those
I
parking
mean,
lots with the parking.
you would say I should
Yeah.
probably like
I think
revisit my
New buildings.
my values.
Yeah.
Yes, you're like,
I like
Exactly, yeah, so if you're part one and part two are.
So, yeah. And I could see them do that, like as things grow, as they're trying to build up.
Yeah.
Okay,
Like,
yeah, you're very close.
this side, go.
Yeah,
Thank you. That side, don't.
because then at that point, all your senior design projects, they can go to the new thing.
Yeah, they plan out to have an area.
Okay, Dr. Weiss is not coming, so we're closing the door.